I represent Group33 to show our group report. The theme we searched for in this project is Apollo Open Software Platform. First, I'm going to introduce the Apollo Open Software Platform. According to our studies, the Apollo Open Software Platform consists of three parts: Apollo, CyberRT, RTOS, and V2X adapter. First of all, Apollo CyberRT is an open-source, high-performance runtime framework specially designed for autonomous driving scenarios. Apollo CyberRT has a well-defined task interface for data fusion capabilities and help user accelerate development by providing a large number of development tool and sensor drivers. To simplify deployment, Apollo CyberRT provides efficient and adaptive message communication and a resource-aware, configurable user-level scheduler with portability with fewer dependencies. This makes Apollo CyberRT better for autonomous driving development. In order to run more efficiently, Apollo CyberRT even has its own basic library at the same time. This runtime framework consists of 4 modules, including map engine, localization, perception, and prediction. For the map engine module, its main function is to load maps in OpenStreet format and provides a series of API for other modules to use. Localization module has 2 functions. One is to output the position information of the vehicle and provides to the planning module, and the other is to output the altitude and speed information of the vehicle and provides to the control module. For the perception module, its function to perceive external information through different sensors and fuse the received information to the planning modules for analysis. The prediction module is divided into 2 categories. The first is the online prediction process, and the second is to extract data for offline testing. Then I will explain the stakeholder in this platform by looking through the GitHub pull request and issue history, as well as the public information from various sources. We have identified the following different types of stakeholders. The first is developer. Most Apollo developers come from Baidu as a research and development center located in California. Other interested developers make a lot of contribute as well, just like most other open source projects. The second is communicator, which is a group of people who explain the system and architecture to others through documents and or training materials. Baidu has a developer center on the official website for this project, and there is a series of tutorial courses. Also, there are some interested users on GitHub build a system project for beginners. As the last one's users, many traditional automobile manufacturers has already become partners with Apollo Object. Some cities in China have also implanted Apollo in autonomous buses as part of their intelligent public transit system. In universities, some students also implant their algorithm on the Apollo platform. That is an example of education use. Before analyzing how Apollo evolved, we must first understand how the system changed between each version. When Apollo was first released in 2017, this platform becomes the world's first open-source platform for autonomous driving. This platform combines vehicles and hardware systems to build a complete set of automatic driving systems. Apollo version 1 has released in July 2017 and a complete full version updated of the following year. Its technical framework consists of 4 labs as shown in the right graph. There's cloud service platform, open software platform, reference hardware platform, and reference vehicle platform. Apollo version 2 improves the cruise part of fixed lines. By adding later plugin, the vehicle can perceive the surrounding environment and pass a convolutional neural network algorithm to pinpoint the location for helping plan route. Version 3.5 optimizes and updates the algorithm under complex road conditions so that vehicles can respond to complex urban traffic conditions by themselves. In September 2019, Apollo 5 was released. It enhanced the autonomous driving capabilities of vehicles in complexity, enhancing the CyberRT architecture, open source and autonomous driving environment framework designed for the cab, targeting high performance, low latency, and high throughput. This architecture has data fusion capabilities, a lot of development tools, and many sensor drivers. It also has portability advantage, efficient and self-adjusting message communication. In version 6, the V2S system has continued to be upgraded, and many previous systems has been integrated. Then we can move to the most concerning part, which is conceptual architecture for Apollo. I will demonstrate this part into two aspects. One is system and the other is interacting parts. Baidu Alpha autopilot system needs concurrent processing of multiple systems. Much depends on its concurrency and resource architecture. The active safety system of automatic driving is the core of this project. The first part is the operating system. It is basic of software that runs on autonomous vehicles that is used to manage, schedule, and control the onboard hardware and software resources. Its main tasks are to provide the automatic driving system with capability of real-time task scheduling, real-time calculation of task resource isolation, real-time message communication, system-level access control. The second part is perceptual system. Environment perception is a prerequisite for autonomous driving. The environment sensing the system integrates the advantage of multiple sensors, such as laser radar, millimeter wave radar, and camera realized 360-degree side distance around the vehicle body and stably detects and tracks information such as the behavior and the speed orientation of the trafficker in the complex and changing traffic environment, providing scene understanding information for decision planning module. The interacting parts include the predictive decision making and planning control technology module. It is equivalent to the brain of an autonomous vehicle. It directly affects the ability and effect of vehicle automatic driving based on traffic safety understanding and consensual rules. The algorithm module plans safe, efficient, and comfortable driving paths and trajectories for vehicles. In order to improve the generalization ability of the algorithm, data mining and depth learning algorithms are applied to realize intelligent planning of driving behaviors. Given the set departure and destination of the vehicle, the system generates the optimal global planning path. Then I will analyze control data and data flow among these scenarios. In Apollo autonomous driving architecture, the control is mainly mastered by the underlying vehicle platform and the sensor layer. The underlying vehicle's platform executes the vehicle control commands and generated by the Apollo autonomous driving platform. In this layer, driving by wheel is the main structure for the control commands. The shifting, acceleration, and the deceleration, steering, and other corresponding operations of the vehicle are all completed through the wire control. After Apollo version 3, drive by wire can be flexibly applied to the Apollo platform through vehicle improvements. Secondly, the sensor layer is mainly used to send commands to the moving vehicles through accurate radar and line of sight monitoring. When the chassis components receive the control command, they will enter the automatic driving state and execute it through CAN bus. This picture clearly expresses the entire process of command and transmission and execution. Regarding the core software platform, we implement both bottom-level real-time operating systems through RTOS. OS2 implements the runtime architecture, then and then followed by data layer to support the provision of upper level modules so as to realize various functions of the Apollo platform. Finally, the cloud service layer is mainly used to provide higher precision map service, simulations, data platform, security, and update. When it comes to the interface of Imagine Data Fusion, digital image imaging converts optical signals into electrical signals. The camera imaging acquisition device is composed of a series of hardware, and the imaging is formed after linear correction, noise removal, exposure correction, and so on. Moreover, the autofocus the algorithm moves the lens to maximize the image contrast through the established imaging contrast. The auto-exposure algorithm automatically sets the exposure value based on the available light source conditions, and the auto-white balance algorithm adjusts the fidelity of the color of the picture based on the light source conditions. The physical principles of camera imaging are pinhole imaging and line imaging. Concentrating light increases clarity, but it will bring mirror distortion, and the distortion correction will basically not affect the accuracy of molecular ranging. The way Apollo obtains data is in the forms of data flow when the real vehicle is running. Anyway, the data flow pattern of the camera perception is just like the imagine shows. Next, I'm going to show some sequence diagram of this research. According to our conceptual architecture, we have composed two sequence diagrams to show our architecture works. The first sequence diagram is the outline of how Apollo software system works, and the second sequence diagram is the extension of the prediction and perception. This is the first diagram, and for the second sequence diagram, or for the first sequence diagram, the user needs to input the destination through the user interface, and then the information of the destination will be input to the map engine, and then judge whether the destination input is correct and transmit the accurate map to localization, which will provide the accurate position of the vehicle according to GPS and other positioning sensors. Prediction is an indispensable module of the whole system because it will obtain the external information of the vehicle through hardware facilities such as obstacles, traffic lights, lane lights, and extra. The collected information will be transmitted to the prediction module to predict what may happen in the future, like the speed of the surrounding objects and the running track of objects. All the information collected by the previous module will be transmitted to the planning modules, which will plan feasible routes for the driving of the vehicle. And then this information will be transmitted to the control module. According to the vehicle status and the planned route, the control command will be sent to CAN-bus to control the driving of the vehicle, and the driving condition of the vehicle during the whole driving process will be reported to the users through the monitor. The whole software system will have a guardian module for monitoring. Once any software or hardware fails, it will take corresponding safety measures. The second sequence diagram is an in-depth understanding of prediction and perception. The whole car have many sensors such as camera, mirror, wave, radar, and lidar. The vehicle will predict and collect information for emergency safety response, such as emergency braking. When the predict information is about to hit an object, slowing down or stopping when a pedestrian is detected, and adjusting the vehicle trajectory when the vehicle deviates from the line. In conclusion, our conceptual architecture encompasses all of the main functionalities that Apollo has to offer. Our Apollo conceptual architecture is a layer architecture, so we propose sub-components of the architecture and can determine the function of each component and their dependencies, concurrency relations. Each of the Apollo architecture interact parts such as predictive decision, binding control, and various hardware, all contribute to the realization for better autonomous driving algorithms. Finally, we will further optimize our sequence diagram based on the feedback from the report, and can further develop the details and internal structure of each proposed subsystem. This is the end of our presentation. So I feel happy to share our researching products with all of you. Appreciate your attention today. Thanks for listening, and here is our reference list.